we have been given the scientific knowledge, the technical ability, and the materials to pursue the exploration of the universe. To ignore these great resources would be a corruption of a God-given ability.
Rocket development has stagnated after 2011 as the NASA Shuttle program ended, causing most of the attention and the budget for NASA to slump. This caused a chain reaction. With a smaller budget, NASA can only conduct less research and development, as seen from the multiple setbacks leading up to the launch of the Space Launch System (SLS) rocket capable of taking humans back to the moon. Since 2009, SpaceX, a private company, has been developing rockets which can land back on the ground after launch. This sort of change can revolutionize the space industry, making it more accessible for companies and governments. When SpaceX's rockets land again, they are checked for wears or fault, mainly the heat shield, which are only suitable for 10 launches. They are repressurized and refueled to launch again. This has been demonstrated many times by SpaceX, who, compared to NASA's average of $152 million per launch, has reduced the cost to only $62 million. When rockets are launched, scientists need to account for many challenges that are faced by the rocket, mainly involving the laws of motion. Sir Isaac Newton's laws of motion can be applied when involving the processes rockets go through while going into space. Newton's first law of inertia states, an object at rest remains at rest, and an object in motion remains in motion at a constant speed and in a straight line unless acted on by an unbalanced force. In the rocket's case, while it is accelerating through the atmosphere, the forces acting on it is mainly its propellant that is propelled from the rocket to achieve lift, friction, and gravity. Gravity continues to act on anything within this mass's sphere of influence. This is a sphere around any object in space where the gravity of the mass significantly affects anything in specific vicinity around it, causing it to have a pull towards the mass. Everything with mass is pulling each other together in the universe, just creating extremely weak forces by their spheres of influence. This gravity force can differ depending on the mass size and the distance within the sphere of influence. The equation to calculate the significant sphere of influence of the planet is below. Once the rocket is in space, it is no longer limited by air resistance and friction, but only the gravity of the planet, and possibly by minuscule specks of debris which could, if monitored, slow down the spacecraft by fractions of a decimal of a meter per second. If the spacecraft has circulated with the planet, it will continue to orbit until it re-enters the atmosphere, due to orbital decay. This is when, mentioned previously, small particles collide with the spacecraft, specifically atmospheric gas molecules, and rarely flecks of orbital debris cause it to lose velocity and orbital altitude and therefore fall out of orbit. Even during the Apollo program, when spacecraft travel in a circularized orbit, in low Earth orbit before traveling to the moon, this orbital decay is only effective over the course of months or years and typically only affects satellites, not excluding the International Space Station. Newton's second law creates another independent variable for the spacecraft through the equation F equals ma. This equation states that the force depends on the mass of the rocket and the acceleration it is traveling. But this is constantly changing because the spacecraft is consistently losing fuel mass and also gaining acceleration. A more suitable equation that describes rocket movement is called the Schilkowski rocket equation. It describes the motion and principles that the idea of the rocket follows. When discussing rockets, delta V is the term used describing the amount of energy involving the change of velocity in the rocket. That equals to the effective exhaust velocity times by the change in mass resulting from the use of propellant. Momentum is another variable that affects the fundamentals of spaceflight and relates as a part of Newton's second law. When a rocket travels into space and finally cuts its engines, it continues to travel away from Earth, following the inertia rule. But over time, it will slow down its acceleration and it will come back to Earth due to gravity. Imagine when rockets travel into space, they create a trajectory like a projectile, which over time, when the rocket is accelerating, gets larger and larger. If the rocket travels upward more, the trajectory will look taller and thinner, while if the rocket travels horizontally, its trajectory becomes flatter and longer, like an aeroplane. Until it gets into an orbit where it overcomes Earth's gravitational pull, the rocket will always have a trajectory towards Earth. But once it has circularized, the rocket will have two important points. the Apoapsis and the Periapsis. The former is the furthest point and the latter is the closest point in relation to the rocket orbiter and the Earth. In SpaceX's case, the Stage 1 of Falcon 9 will not get to this stage and will continue back to Earth to its desired landing site. The second stage will continue to circularize around the Earth using an orbital insertion burn. When considering artificial satellites, making the Apoapsis and Periapsis as similar as possible allows the most stable orbit to be sustained. Newton's third law is whenever one object exerts a force on another object, the second object exerts an equal and opposite force on the first. Rockets use rocket fuel which is practically exploded behind the rocket with a large force. This generates enough energy for the rocket to overcome its mass and gravity during liftoff. But as the rocket continues flying with an emptying tank, its rate of acceleration increases as there is less mass to push. These propulsion factors all change when the rocket reaches space, as specific and accurate maneuvers need to be made all the time from creating exit burns or to rendezvous with satellites. This is when small engines are needed, mainly a larger engine acting as the rocket's main propulsion, and the RCS thrusters, which can tweak the rocket's direction to make sure it stays on course. Science is a human endeavor. One common aspect which is seen through all rockets and most technology is control systems. These systems use sensors and communication relays to monitor many variables of the rockets during flight, and according to the code already written, uses this information to make changes to its trajectory by controlling systems around the vessel, part of SpaceX's Altitude Control Systems, ACS. ACS enables the dynamic launch, maneuvering, and landing of SpaceX rockets. In the last decade, SpaceX began with launching test rockets which hovered in the atmosphere and attempted to land again on the ground using included landing gear. With the final successful test of the first Falcon rocket, shortly the Falcon 9 was built and tested thoroughly, as it is still being used today to enable satellite missions for private companies and SpaceX's other ventures. After perfecting the landings of the Falcon 9, a bigger rocket was produced called the Falcon Heavy, which combines 3 Falcon 9 boosters, making it the most powerful operational rocket today, following behind the Saturn V. Most recently, a new rocket has been conceptualized and created called the Starship. Over the last few months, Starship prototypes have been launching under the names SN, and on the day of writing this, the SN-15 test was fully successful with landing the improved prototype after a nosedive from 10 kilometers in the sky. This is an important part in securing the Starship as the next rocket alongside the SLS to take humans to the Moon and Mars, but for these rockets to be sustainable, they need each booster to land and be reused. These landings are created from the prime aspect of testing, trial and error, which is also a completely different learning technique compared to NASA. This is partly due to the rocket's reusability. NASA's limited restrictive budget and its consistently changing policies from the government affect NASA's ability to build and test. The Falcon 9 rockets use 9 Merlin engines that use Gimbal to give stability and control to the vessel. Gimbal is the act of moving the engine slightly to enable changes in the trajectory of the rocket. This is done using the hydraulic systems on board, which when applies enables further accuracy when landing and during takeoff. An example is the Falcon 9 constantly changing velocity to get into orbit. Another application is the landing gears. On the Falcon 9 and the new Starship, they are retractable and are retracted out on landing, allowing the rockets to land without any damage or wear given to fragile parts of the rocket, promoting the rocket's reusability and preventing costly structural repairs. Another control on the rocket, RCS mentioned before, is the reaction control system. These are small propulsion engines that surround the rocket and are increasingly effective in space, although they are used in the atmosphere. They propel gas which allows the rocket to make minor adjustments to its trajectory in space. In the case of the Falcon 9, the thrusters point the rocket in the direction it needs to be before going below into the atmosphere where they won't be as effective. A final control is the grid fins on the Interstage, connecting the 2 stages of the rocket. Falcon 9 uses grid fins which act to stabilize and adjust the directions of the rocket during atmospheric freefall, changing the Falcon 9's effective landing accuracy range from 10 kilometers to 10 meters. The Starship has similar controls near the nose cone, but are in a winglet shape, allowing it to withstand larger forces which are experienced during the re-entry of the rocket, whilst creating more drag similar to fighter jet winglets. These connect to the control systems, which update trajectory constantly and find the direction the rocket needs to point to land at its intended landing site. This allows the rocket to maintain structural and software functionality. I created interview questions which I would have asked Elon Musk if I had the opportunity to interview him. They are listed on screen now. With SpaceX's advancements, the next decade is very promising for spaceflight. From current predictions, these include the foundations for a lunar and Mars colony. This will be the very beginning of a long line of advancements which will be created from the challenges that will be set in the near future. Investing in space tech is becoming an even more lucrative investment, but with more things happening in space, more things have the chance to go wrong, which humanity will need to prevent and to persevere through. Thank you for watching my video.